quantization. So what is important here? We still have an input signal and a sampling frequency that we can play with, but now we can play with the bit depth. It means the number of bits we will use to quantize this analog infinite number of voltages of the input signal into a finite number of bits. So in this case here, you see again a 440 hertz input signal sampled, in this case again the original loading parameter of 48 kilohertz. Obviously there is no problem, the signal is way below Nyquist here. Nyquist in this case would be 24 kilohertz, right? So there is no problem. I'm using 16 bits by default, and I have absolutely no issues here. So I have 65,536 different levels to choose from, etc. So what happens now if I start reducing this bit depth, so using less bits to quantize this signal? So of course, I still have, for instance, here 1024. I barely see any changes in the graph here, but also I still have a lot of levels, right? I mean, it could be obviously a problem with real audio, etc., but in this sinusoid here, in this example, it's still okay. Let's continue reducing this. And now you see on this graph here on the left, this the middle one, you see that the number of horizontal lines reduce. For 5, I have 2 to the power of 5, 32. 4, 16, 3, I have 8 levels only. So what happens in the quantization is exactly that now any sample taken here has to be, the value of this sample has to be associated to one of only 8 values. And of course you start seeing here the noise. The more I reduce the number of bits, so the less the levels I have, the more the difference between an ideal position, the original analog voltage, and the quantized value will be. So this is reflected here on the noise, and that actually is reflected here on these small peaks on the frequency domain where you see basically distortion, right? So again, the more I reduce, so if only 4 levels now, you see that there is substantial distortion that can be heard actually. This is the original signal. And this is what happens with the distortion. Right, and this is because, not because of aliasing or sampling, it's because of I'm not using enough levels, bit depth, to quantize my signal. Right. So one way to solve this, not to solve, but to reduce this distortion effect, is to add Dither. And Dither is this noise that actually helps move around values into the small number of levels and actually decorrelate the distortion, right? The result from the process. So, but I get noise. So let's listen to the original again. It didn't change. And now let's listen to the result with Dither. So there is noise, but at least I hear less distortion here. And you can see that the graph here is less regular, right? Again. Right, so basically I have a lot of noise, but I don't have the distortion. So if I take Dither out now, the graph becomes regular, indicating there is probably different components related to the original signal distortion. Right? So again, this is a kind of trade-off between noise and distortion. Right? Then of course you would apply a Dither that's not so strong, etc. But that's the principle, right? Decorrelating the error from the signal.